Neutron stars are fascinating objects. They are incredibly dense remnants of massive stars. Imagine squeezing the mass of our sun into a sphere with a radius of only a few miles. That's the incredible density of a neutron star. A teaspoonful of neutron star material would weigh billions of tons on Earth. These extreme conditions make neutron stars natural laboratories for studying physics. Neutron stars form when massive stars exhaust their nuclear fuel and collapse. The collapse triggers a supernova explosion, briefly outshining an entire galaxy. Protons and electrons in the star's core form neutrons. These neutrons create an object of unimaginable density. Neutron stars emit powerful beams of radiation. These beams sweep across space like cosmic lighthouses. When these beams point towards Earth, we detect them as pulsars. The discovery of pulsars in the 1960s provided evidence for neutron stars. Neutron stars play a crucial role in our understanding of the universe. When stars reach the end of their lives, their fates are determined by their mass. Stars like our sun will shed their outer layers, leaving behind a dense core known as a white dwarf. White dwarfs are supported by electron degeneracy pressure. There is a limit to how much mass a white dwarf can support. This limit, known as the Chandrasekhar limit, is about 1.4 times the mass of our sun. Exceeding this limit results in a type Ia supernova. These supernovae are incredibly bright and serve as standard candles for measuring cosmic distances. Stars significantly more massive than our sun face a different destiny. Their cores collapse further, overcoming electron degeneracy pressure. This collapse forms neutrons. This process creates a neutron star, denser than a white dwarf. The distinction highlights the crucial role of mass in stellar evolution. While both are remnants of dead stars, their vastly different densities and properties are a direct consequence of the initial mass of their progenitor stars. Neutron stars are born from the fiery deaths of massive stars in spectacular explosions called supernovae. When a star significantly larger than our sun exhausts its nuclear fuel, it can no longer generate the outward pressure needed to counteract its own gravity. This imbalance triggers a catastrophic collapse of the star's core. As the core collapses, it rapidly heats up, reaching billions of degrees Celsius. This intense heat and pressure cause the core to release a tremendous amount of energy in the form of neutrinos. These ghostly particles escape the core, carrying away a significant portion of the star's energy. The remaining core, now composed mostly of neutrons, continues to collapse until it reaches nuclear densities. This sudden halt in the core's collapse creates a shock wave that propagates outward through the star's outer layers. The shock wave, powered by the escaping neutrinos, tears through the star, blasting its outer layers into space at incredible speeds. This violent explosion is what we observe as a supernova. The remnant of this cosmic explosion, the incredibly dense core, is the newly born neutron star. Supernovae are not only responsible for seeding the universe with heavy elements, but also for creating some of the most extreme and fascinating objects known to science. For decades, astronomers could only study neutron stars through their electromagnetic radiation, such as radio waves, X-rays, and gamma rays. However, a new window into the universe has opened up in recent years: gravitational wave astronomy. Gravitational waves are ripples in the fabric of spacetime, predicted by Einstein's theory of general relativity. These ripples are generated by the acceleration of massive objects, such as neutron stars or black holes, particularly when they are in binary systems and spiraling towards each other. The first direct detection of gravitational waves, announced in 2016 by the Laser Interferometer Gravitational Wave Observatory, LIGO, marked the beginning of a new era in astronomy. Since then, LIGO and its European counterpart Virgo have detected dozens of gravitational wave events, many of which involve the merger of two neutron stars. These detections allow astronomers to study the properties of neutron stars in unprecedented detail. By analyzing the gravitational wave signals, scientists can determine the masses and spins of the merging neutron stars, as well as the properties of the extremely dense matter that makes up their cores. Gravitational wave observations also provide insights into the nature of gravity itself, testing Einstein's theory in extreme environments. As gravitational wave detectors become more sensitive, they promise to reveal even more secrets about these enigmatic objects and the universe we inhabit.